So hello everyone, myself Hrishikesh, and today we are going to talk about unveiling the invisible, that is advancements that are happening in transparent object post-detection and estimation. So first of all, why do we even need to care about transparent objects? Well, because they are basically everywhere. In industry, maybe in the drinking industry or maybe in water industry, you can find a lot of those glass bottles on the conveyor belt, or maybe in some big Amazon warehouses regarding robot pick and place, you're going to find a lot of transparent objects. In the medical automation industry, of course, most of the sterility kits, like test tubes, the syringes, and the glass bottles, like canisters and stuff, they're mostly transparent. For the household, yes, we can also find a lot of transparent objects in our daily household items, and especially if you're trying to make a robot, which is with the goal of actually trying to tidy up your house, it has to deal with transparent objects. Of course, also in the service industry, maybe there is a robot trying to pour a glass of water to the customer. But why is post-estimation necessary? Well, it appears that if a robot wants to grasp a particular object, it needs the 3D translation and the 3D rotation from its actuators to the object. And this set of 3D translation and 3D rotation is what we call the 60 pose of the object. So a typical grasping pipeline would look as follows. The robot would need to detect the transparent object in the 2D image, and then we need to do the 6D pose estimation of that object, and then finally the robot can grasp. But what is so challenging about transparent objects? Well, as you can see in the set of transparent objects, in the set of images of a transparent object, either the transparent object is not visible because of its transparency, or its appearance is heavily dependent on the viewing angle or on the background of the camera. Well, for opaque objects, that's not the case, and you can see that very well in the opaque object set of images. One of the key requirements for either doing pose estimation or grasping a particular object is its depth information. And for transparent object, it's actually pretty bad. Like, we get a lot of bad and erroneous depth for transparent object. And that's mainly because whenever the depth sensor sends, let's call it a depth trace through the transparent object, it either passes through the transparent object and it reports the background depth, which is the type 1 error you can see, or the ray never comes back because of the refraction and reflective properties of the transparent object. And that's why depth is pretty bad for a transparent object. But as you can see, for opaque objects, it's quite well defined. So for opaque objects, it's not a problem, but for transparent object, it's still a big challenge. So how do the current state-of-the-art methods, which are out there, are performing when it comes to 6D pose estimation of transparent object? Well, actually not that good. Because as you can see in the top row of images, you can see the input image of the transparent object. You can see the ground truth pose of the transparent object, and how the two most well-known methods, that is the CDPN and PVNet, performs for the transparent object 6D pose estimation. We also did some grasping experiments in our lab. We trained COPE, which is which is state-of-the-art 6D pose estimation method published last year in our lab. We did the 6D pose estimation of the canister, and we tried to grasp the transparent object. And as you can see, the robot completely failed to actually grasp the canister. And that's mainly because these methods, like COPE, CDP, and PVNet, they heavily rely on the RGB features or the depth features of the transparent object. So usually there is a 3D translation error while grasping these kind of objects. So what are the current research trends in transparent object pose estimation? Well, it can roughly be divided into three categories: the depth-based methods, the indirect depth-based methods, and extracting the geometric shapes of the transparent object. In the depth-based methods, the clear grasp, the first two methods that are the clear grasp and RGBD local implicit function method, They don't actually do the pose estimation, but what they do is that they try to take the erroneous depth, input depth of the transparent object, and they try to refine it and recover those erroneous depth. And this method can directly be used for grasping or further pose estimation algorithms down the line. Clear pose actually does a 60 pose estimation of transparent object, and what it does is that it takes the input image, it takes the erroneous depth of those transparent object, and either using trans-CG method or clear grasp method, it tries to refine the input erroneous depth and uses FFB60, which is a well-known pose estimation method, for actually doing the pose estimation of the transparent object. Key pose, I put it in the category of indirect depth, and that's mostly because it does not actually do depth estimation directly of the transparent object, but it works with the stereo images, so it has an indirect depth information through the disparity map. And what key pose does is that it actually doesn't do a full 60 pose of the transparent object, but it tries to actually detect the key points. So now to explain you what exactly is the key point is like, it's one of the easiest way to describe, or one of the simplest way to describe the geometry of an object. So for example, here the bottle has 2 key points. A triangle would have the 3 key points. So that's how the geometry is defined. So key pose does the key point detection of the transparent object, given the 2 stereo images. TGFnet is one of the most recent methods in the 60 pose estimation of transparent object. It was just published 1 month ago, and what it does is that it takes the input image of transparent object, it extracts the geometric features, as you can see here, for example, the contour of the transparent object or the boundary of the transparent object, and it tries to estimate the pose from it. So while all the other methods are directly estimating the 60 pose from the input RGB, the TGFnet actually tries to derive the pose from these geometric features, and that's why it's performing better than all the other methods. Through the looking glass, it's also, I put it in the indirect depth, and it's very different from all the other methods, and that's because it doesn't do pose estimation, neither it does a direct depth estimation of the transparent object. But what it does is that given a few set of input images, like 5 to 20 number of images of a transparent object, it tries to build a full 3D model of the transparent object or reconstruct the full 3D model of the transparent object. So in a way, it does learn some form of indirect depth estimation of the transparent object, which can also be useful for further research. But what are we doing different? Well, we are making neural network to learn actually the physics-based features of the transparent object. So we are modeling the physics of light interacting with the transparent objects, and we are making the neural network actually learn these features and extracting the full 60 pose from it. And how do you perform when it compares to this? Well, we are actually performing a bit better as compared to the current state-of-the-art GDRNet method, which was published last year and it's highly used in the field of 60 pose estimation methods. You can see we are improving like 45%. And on the right side, you can see the qualitative comparison. In the top row, you can see the input image. You can see the zoomed view of that. You can see the ground truth pose, the predicted pose from our method. And in the last row, you can see how it performs as compared to the prediction in ground truth. So in conclusion, yes, transparent objects are tricky, but because they're everywhere, it's necessary to have accurate pose estimation of these transparent objects. The 3 main research trends being depth completion, indirect depth estimation, and geometric features-based methods. And we are taking the approach of modeling physics-based features and estimating the pose of those transparent objects instead of directly estimating them from the RGB images. And yes, we can grasp the invisible. I don't know how to play the video.